Okay, I'm going to get into 3 examples in 3 videos of kind of unusual divergence theorem situations. So I'm going to first talk about using the divergence theorem to evaluate surface integrals which are not of f dot n form. So let me just give you a concrete example of this. So let's consider the surface integral of x plus y plus z ds. So notice it's not of this form. ds does not have a vector, and there's no f. This is a scalar. And so you might be wondering, how on earth do I apply the divergence theorem to something like this? The key observation is that f dot ds is also a scalar. So you can actually cook up an f to make it equal to this expression. So our problem now is to find f such that f dot n is equal, f dot n ds is equal to x plus y plus z ds. So in other words, f dot n is equal to x plus y plus z. And let me just specify the surface. It'll be my favorite surface, x squared plus y squared plus z squared equals 1, the unit sphere, whose normal vector is just the position vector divided by its length, which happens to be 1 in this case. So it's just x, y, z. Okay? So in other words, we want to find f such that f dotted with x, y, z is equal to x plus y plus z. So, I think the simplest choice is just 1, 1, 1. Right? So we've now found that our integral can be represented like this. It's 1, 1, 1 dot ds. So this is our f. And so now we can evaluate this using the divergence theorem. We have our triple integral of del dot f dv. So notice that the divergence of this constant vector field, just like the derivative of any constant, is just 0. So we've actually shown that this integral is 0 in an almost trivial way. But it's not as obvious if you look at this integral, is it? Could you have said that was 0 instantly? You could argue by symmetry, but it's clearly not obvious. So the divergence theorem is often very helpful for evaluating surface integrals. Thanks for watching.